This is the second video on capacitors. Now we're going to talk a little bit about charging capacitors. We're going to talk about energy, uses of capacitors, and we'll quickly look at the use of iterative methods as regards capacitors. Charging a capacitor, I would use this circuit here and make sure the capacitor is uncharged to start with. You can do that by just short-circuiting it. Then when you close the switch, the capacitor will charge. And this is a graph of charge against time for a charging capacitor. The charge on the capacitor will vary like this, as will the voltage across the capacitor. The current and the voltage across the resistor will still fall exponentially, however. A good analogy for this is if you imagine eating as many biscuits as you can as quickly as possible. And if you plotted a graph of biscuits eaten against time, it would, well, possibly look similar to that graph. Energy stored on a capacitor, this is a good way of investigating that. If you charge up a capacitor and then use it to discharge it through a motor, which is lifting a mass, and look at how high the mass is lifted. And then you can investigate the difference it makes when you change the capacitance and when you change the voltage, the charging voltage. This experiment can show that the energy stored is proportional to the capacitance and it's proportional to V squared. Important, remember, it's proportional to V squared. These are the equations. Energy stored is a half QV equals a half CV squared. Where do these equations come from? Well, imagine we plot a graph of Q against V. We get a straight line because Q equals CV, and it's the area under the graph is equal to the work done charging the capacitor, and therefore that is the energy stored. So a half QV, and if you sub for Q, you get a half CV squared. The argument is it's the sum of lots of little rectangles, lots of Q delta V's. Not too bothered about that, but do remember that it's the area under this graph. Uses of capacitors, well, storing energy when you need a burst of energy, for example, a camera flash or a defibrillator, what you do is you charge up a capacitor and then you discharge it. However, capacitors are used in timing circuits. Because a capacitor takes time to charge and discharge, then in circuits where time is involved, for example, the clock circuit in a computer, then a capacitor will be involved somewhere, probably with a 555 chip. In AC circuits, capacitors act like resistors. You often find them in power supply circuits. You find them in what we call filter circuits because, as I say, they act like resistors, but their resistance depends on the frequency. So they have a property called reactance, which is measured in ohms, and this property reactance is frequency dependent, and you don't need to know that. Now, an iterative method. Iterative means doing it bit by bit. You can work out the charge on a discharging capacitor using an iterative method if, for very small time intervals, delta t, you assume that the discharging current is constant. You work out delta Q using this equation here. Delta Q is minus Q over RC times delta T. You take that away from Q, and then you do that again and again and again, and you can get an approximation of the charge on the capacitor, how it varies with time. How accurate is this method? The accuracy of the answer we get is very much dependent on what time interval we use. Because we're assuming that the discharging current is constant, but it isn't constant, it falls exponentially. So the bigger the time interval, delta t, then the less accurate our answer will be. Here's an example you should have a go at. A 470 microfarad capacitor is charged to 10 volts, then discharged through a 1K resistor. Complete the values in the table. Explain why the charge remaining using this method will be less than from using that equation. how might we get a more accurate value? So I suggest you pause the video, have a go at it, and these are the answers. I've worked out the values of delta Q. I've used those to work out the values of Q. For each 0.1 second interval, we are making an assumption that the discharging current is constant, where in fact it isn't, it's decreasing exponentially. So all of our values of delta Q will be too big. If we use a smaller value for delta T, then the difference would be smaller, so we would get a more accurate answer.